Good morning. Today we're going to talk about dipoles, electric dipoles. So what's a dipole? Well, it's a positive charge, show that here, and a negative charge. Simple as that. There's my negative charge. And let's just think about what the electric field of a dipole will look like. I'll have electric field lines coming out of the positive charge, going into the negative charge. There's an example of an electric field line. Here's another one. Here's another one. Maybe here's another one. But then I'll also have electric field lines that come off the positive charge and go away to infinity like this. And I'll have electric field lines coming in from infinity into the negative charge. And if I've drawn this right, there should be the same number of field lines coming in from infinity. I've got 1, 2, 3, 4, 5. The same number of electric field lines going out to infinity, 1, 2, 3, 4, 5, because this entire object is neutral. It's one plus charge and one minus charge with a total charge of 0, and this is what we call a dipole. Now, why do we care? Why are we interested in dipoles? Why are we going to talk about them as special objects whose behavior we're going to learn to understand, as opposed to just thinking about them as one plus charge and one minus charge, nothing more to say? The reason is that everything around us is neutral, and this is the simplest neutral object we can make in 802. It's all well and good to talk about charged Van de Graaff generators, to talk about charging me up and making my hair stand up. That's fine. But most of the time, almost every object that we encounter in the natural world and in technology is neutral. It's made of equal amounts of plus and minus. And a dipole is the simplest neutral object. And so what we started 802 with was Coulomb's law, where we had a plus charge, and we talked about its field, and we talked about the forces that it caused and felt. And we had a minus charge, and we did the same for a minus charge. But you very rarely encounter isolated plus charges or isolated minus charges. Almost everything you bump into is neutral, and so we need to start thinking about neutral objects, and the simplest neutral object is a dipole. We're talking about dipoles today, and I already said, why are we interested in dipoles? Because we're made of dipoles. We're not made of isolated neutral, plus charges or isolated minus charges. Another way of thinking about why we talk about dipoles is to say, well, suppose we actually, for some reason, start with a bunch of charges. Okay? There's a plus, and I'm trying to put these down in random locations. I don't want them to be in any kind of like a perfect square or anything. I'll stop when I get to 4 of them, 2 pluses and 2 minuses. So there is some pretty random location of 4 charges. Now, what's going to happen if we have minus charges here and here, plus charges there and there? Well, the first thing that's going to happen is that the charges are going to feel their closest neighbors, and a plus is going to be attracted to a minus. So the very, very first thing that's going to happen very quickly is that the plus and the minus are going to get pulled towards each other, and we're going to end up with a situation like this. And these two are going to feel each other, pulled towards each other. And so really quickly, we're going to end up with a situation like that. And at that moment, we have 2 dipoles. So we started with 4 charges at 4 random places, and very, very quickly, by the Coulomb attraction, we end up with 2 dipoles. And this is the generic thing that will happen unless you make some very special arrangement like a square, for example, where something different will happen. So right now, I have 2 dipoles. Each one of these has electric fields. They look something like the fields that we drew over here, but on a smaller scale. So there's white field lines between these 2 and around these 2. There's white field lines between these 2 and around these 2. And now I have 2 dipoles. And what we are going to learn to understand today is what happens next. What are the forces between the dipoles? How do they interact with each other? What do they do? Okay, so now we ask ourselves, what's going to happen in a situation like this? We have these 2 dipoles. The electric field from this dipole is going to exert a torque on this one, making it turn. And the electric field from this dipole is going to exert a force on this one, making it turn. We're going to do the calculation later. We will see how electric fields make dipoles turn. We will see how dipoles themselves make electric fields. You can already see that. We already saw that. This dipole is making a field. Each of these dipoles is making a field. And we'll see later the math that will show us that a field makes a dipole turn. So what's going to happen is that this dipole is going to turn, and we'll end up looking like this. And this dipole is going to turn, and we'll end up looking like this. And the dipoles will turn until they're aligned. So first the dipoles formed very quickly, then more slowly, each torques the other, and they turn until they're aligned. And then even more slowly they attract each other. Once they're lined up like this, there's a weak force. Even though this is neutral, and even this is neutral, they have electric fields. These neutral objects have electric fields that look like the electric field of this. And the field of this one will pull on that one, and the field of this one will pull on that one. Very slowly, more slowly than the time it takes for them to torque and align, they will attract each other, and at the end, we'll end up with a configuration of 4 charges that looks like this. A positive, a negative, a positive, a negative, and a positive. So the math that we need to do now, we need to understand the field that a dipole makes. I showed it to you here. We then need to understand how an electric field created, however it's created, makes a dipole turn in a certain way. And then we need to understand how an electric field pulls a dipole, not with anywhere near as strong a force as a naked charge would, but pulls a dipole so that 2 dipoles can pull each other together, and at the end we end up like this. So why might you be interested in this? Well, this is at a cartoon level, in a very simplified level. This is what happens with atoms and molecules in your body and in the world around us. Every water molecule is a dipole. So when I talked about the forming of the dipoles, that could have been forming of water molecules. Now, it's true that the molecules I used here had only 1 positive and 1 negative, whereas water is 2 H's and an O, so water is a little more complicated than this. Maybe this is something like CO, carbon monoxide. So the first thing I described was the formation of the COs. Then they felt one CO felt the presence of another, they lined up, and then they attracted each other, and we ended up with a larger molecule. So you can think of these electric interactions between dipoles as being the very beginnings of chemistry. Chemistry there's much more to chemistry than just dipoles, but this is the beginnings, this is the germ of chemistry. This is the very beginnings of chemistry. And more generally, this is the beginnings of how charged particles behave in any real situation, because they're never isolated. There are always other charges around. The first thing that happens always is you form dipoles, and then the dipoles interact. You can get more complicated structures than this. There's more to the world than 2 pluses and 2 minuses. For example, maybe you'll have 2 of these objects. So here's a second one. There's a positive charge, and there's a negative charge, and there's a positive charge, and there's a negative charge. And we could now start asking, what's the field of this object? What's the field of this object? How do these 2 interact with each other? Do they turn each other? Do they attract each other? We could start looking at the attractions between more complicated objects still, with different shapes. In 802, we're only going to go as far as the mathematics behind dipoles, how dipoles, what their field is, how they interact with each other, how they torque each other, how they pull each other. But I want you to understand that this is the beginning of a journey which leads you from simple elementary objects with 1 plus or with 1 minus to dipoles, then to several of these, then to more complicated objects. This is the beginning of a journey to understanding how complex forms of matter emerge from simple underlying laws, like the laws of electricity and magnetism. Okay, so last time we began to learn about the physics of dipoles. Let me remind you what a dipole is. Dipole is 2 charges a negative charge that I'll put right here, and a positive charge that I'll put right here. And by convention, we are going to refer to the separation between the two charges as 2a. So this distance here from one charge to the other, we will call 2a, a being some quantity with the units of length. And what I want to do now, as the first step towards doing a quantitative analysis of the physics of dipoles, how they move, what forces they feel, what torques they feel, is I want to introduce a quantity called the electric dipole moment, which is a measure of the strength of a dipole. And I will introduce it in the context of an arrangement of charges, which is simply the simplest possible case where there is a dipole moment, which is two charges, a negative charge and a positive charge. I'm going to refer to this lower charge, this negative charge, as Q1, and Q1 is negative. So I will think of Q1 as minus Q, Q being some quantity of charge. And this upper charge here we'll call Q2. Q2 is positive, so Q2 will be plus Q. So I'm choosing a configuration of charges in which the magnitude of the two charges are the same. Their signs are opposite. This one is positive, this one is negative. They're separated by a distance 2a. And we can now define the electric dipole moment, which is represented by a vector p. So this is the electric dipole moment. And its definition is, for a case like this with only two charges, its definition is simply Q1 R1 plus Q2 R2, where Q1 and Q2 are the two charges. I've already told you what those are. But now, what are R1 vector and R2 vector? R1 vector and R2 vector are vectors from the origin to charge 1, from the origin to charge 2. Well, what origin? As I will explain at the end, it doesn't actually matter where I put the origin. But for simplicity and convenience, I'm going to put my origin right there, right in the middle between the two charges. And I'm going to pick a coordinate system now. I'm going to pick my x-axis to run this way, my y-axis to run this way. And that means that I have, in terms of unit vectors, I have a j-hat vector that points up and an i-hat vector that points this way. So with that definition, I now can draw my R1 and R2 because I've picked an origin. R1 is the vector from the origin to charge 1. So this is R1. And R2 goes from the origin to charge 2. So this is R2. And once I have these definitions, I've got R1, R2, Q1, Q2, I can now evaluate the electric dipole moment of this configuration of two charges. So it's Q1. What's Q1? Q1 is minus Q times R1 vector. What's R1 vector? Well, R1 vector is a vector whose length is a and whose direction is minus j hat. So I have a and then a minus j hat plus Q2. What's Q2? Well, Q2 is plus Q. What's R2? R2 is a vector that points in this direction, so it's in the plus j hat direction, and once again it has length a. So I have Q, a, j hat. And you see two minus signs here, minus minus, that makes this plus, so these two terms add. And so we end up with an electric dipole moment given by 2 times Q times a times j hat. And this is, in fact, our result for the electric dipole moment of this very simple configuration of two charges, one positive and one negative. And what do we see in the result? Well, we see a vector that points from the negative charge towards the positive charge. It's pointing in the j hat direction. That's this direction here. So the dipole moment vector always points from the minus charge to the plus charge. And what is the length of this vector? Well, it's Q. Q is the magnitude of the charges at the two ends, times 2a. 2a is the separation between the two charges. And so this generalizes. If I have some other dipole over here, here's my negative charge, and here's my negative charge, and here is my positive charge. Then the dipole vector for this dipole will be a vector that points in this direction. And the magnitude of this dipole vector, electric dipole moment, the magnitude of this dipole moment will be given by Q, which is the magnitude of the charges at the two ends, times this separation between the two, and the separation between the two we are going to be calling 2A. 2A again being this distance here. So last point, I said it didn't matter where I chose the origin. Let me just convince you of that. So suppose I had been perverse and made my life difficult by choosing my origin here. Why on earth would I pick the origin there? Well, I just want to show you that it doesn't matter. If I had picked my origin there, if I'd been made my own life difficult by doing that, I'd have a new R1. This would be my new vector R1, and I would have a new R2. This would be my new vector R2. But if you look at what occurs in the expression for the dipole moment, it's Q1 R1 plus Q2 R2, but Q1 and Q2 have opposite signs. So the vector that comes in here is the vector given by R2 vector minus R1 vector. So when I go back over here and I do R2 vector minus R1 vector, that gives me a vector which connects the tips of these two and points in this direction. So no matter where I had picked the origin, I would have gotten the same result for the electric dipole moment. I would have gotten, for this particular configuration, I would have gotten 2qa times j hat, even if I had put the origin there and made my own life difficult. So the electric dipole moment can be defined for configurations with more charges. This definition generalizes. You will have Q3 R3 plus Q4 R4 dot, 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 and you'll see that next. But this is the simplest case with which to introduce this definition, and so for today we will stop here.